Alright, hi everyone. This is the second video on the introduction for chapter 3. We will see in this video some concept that we need to understand in order to apply Gauss' law. So the first concept we need to talk about is the concept of electric flux. Now recall from chapter 2, we talked about the electric field line being emitted by a positively charged particle. So we have a charged particle, it's a positive charged particle, and it emits electric field line outward. Well, the concept of electric flux is the concept of counting the number of electric field line going through a surface. So let's look at a basic diagram. We have an electric field, it's moving in the positive x direction, and it crosses a surface. And the idea of the electric flux, as I said, is to count how many line there is. All right? So basically we will compute the electric flux multiplied by the surface area. Now there's a small problem with this is it's possible to have a tilt surface also. So we need to take that into consideration. And in order to do these type of calculation, we need to introduce a new mathematical tool, the area vector. So the area vector is a vector that is perpendicular to the surface, perpendicular to the area we are considering. The magnitude of the area vector is simply the area itself. Now, the reason we use the area vector is so that we can use the dot product to calculate the electric flux. All right, so let's see. The electric flux, we use the letter phi, is equal to the dot product between the electric field vector multiplied by the area vector. Now, you don't really need to remember that part. In all the situations we are going to consider, there will be a way to simplify this calculation. You do need, though, to remember that part. So the electric flux is equal to the magnitude of the electric field multiplied by the area, or the surface area, through which the electric field goes through, multiplied by the cosine of the angle. Now, let's say the most challenging part of that equation is figuring out which angle we are talking about. And when we look at the second diagram over here, it is the angle with respect to the vertical. Now, the way I like to see it is we are calculating the effective surface through which the electric field are going through. So you can imagine we are initially, our surface has an angle of 0, like here. There's a maximum number of field line going through it. But if we start tilting the surface, there's less and less field line going through it, all right? And to get a ratio of how many field line we are losing, in a sense, we need to use the cosine. So the effective surface would be that side over here. So all the field line, let's say, going above will be missed in this case, all right? So recall, electric flux is equal to the magnitude of electric field multiplied by magnitude of the area vector, which is simply the area itself, cosine of the angle with respect to the vertical. All right, so just to let you know, it's possible that you get a question like this in the test where I give you the angle over here instead. So make sure to do the conversion. If you get the angle over here, well, this one is 90 minus this angle. We will do some example using that concept. The second concept we need to talk about is the concept of a closed surface. So not exactly a concept of a closed surface, but what happened to the electric flux when it goes through a closed surface. So let's imagine we have a closed surface over here. Now, this is in reality a 3D surface, and it is closed. Now, it's hard to draw a 3D surface on a 2D board, so you have to use your imagination here. But we need to define the sign. Is it a positive or negative when the electric field is going through a surface? And the convention we're going to use is if an electric field line is going in a closed surface, the electric flux is negative. If an electric field line is going out of a closed surface, it is positive. If we have a closed surface without any charge inside, well, the number of field line going in and out will be identical. In other words, the net flux coming out of a closed surface will be 0. The other case is we have a charge inside the closed surface. So let's look at what would happen if we have a positive charge inside the closed surface. Here we have a positive charge. Remember, it emits electric field line outward. So we have many lines crossing the surface. All these lines contribute to the positive flux going outside. Now, as we've seen in the previous case, all the electric field line coming from charge outside the surface do not affect the total flux going through the surface. So in this case, the electric flux will not be zero. And since only the charge inside the surface is responsible for the electric flux, there is a link we can use to know what is the total electric flux, and that is Gauss' law. So Gauss' law links the electric flux with the charge inside a closed surface. The electric flux is equal to the total charge inside the surface divided by epsilon zero. And I added, this is the total flux going through a closed surface. It has to be a closed surface. If it's not a closed surface, let's say you're missing a piece, it's a half sphere, well then there's a couple of lines that are not going through any surface. It has to be a closed surface. We will see many examples where we can use that concept to calculate the electric field inside the surface, or to calculate the electric field for objects that are not that it will be hard to calculate without Gauss' law. So I'm thinking about cylindrical object and a very big planar object. All right. So in the next video, I'm gonna talk about symmetry in the case where we can use Gauss' law to solve these kind of problems. So see you in the next video.